Ladies and gentlemen, welcome to the beauty and joy of computing. Woo! I'm so happy to be here. My name is Dan Garcia. I'm a teaching professor in the EECS department. I've been here for 35 years. I helped build this course with my colleague, Brian Harvey. This is such an exciting semester, the fall 2024 semester. What I wanted to do was give you a chance to watch the first video online because I'm going to be in Detroit giving a talk when my dean asked me to join her on stage at the Nexus Summit that's happening in Michigan. So I have to be in Michigan with my dean. So I'm missing the first day of class for the first time ever in 35 years. And so I wanted to record this video so you could watch it in advance. And then my awesome head TA, Victoria, is going to give the second lecture on the first day of class. So this is the welcome lecture you would have gotten normally, but I wanted to make sure you got a chance to get this early. So I'm so happy to be here. So hopefully you just watched in the playlist the wonderful, inspiring video of students talking about how BJC has been impactful for them. Please watch it over and over again to get psyched about the course. These are former students who weren't told what to say, but just got excited about it and said, I need to share how powerful BJC was for me, Beauty and Joy Computing. So I'm happy to be here and happy to share that with you. Let's get into it and let's talk about our class. All right. So I want to say you're taking a class that was featured in the New York Times, huh? With the New York Times. Okay. 2017, the New York Times came and did a feature piece on our class and talked about me and our class and how we teach abstraction and milkshakes. And I'm going to get to that today. So we're actually going to cover this material today. Pretty exciting. All right. In one slide, what is this course about? You're going to learn the big ideas of programming, abstraction, algorithms, recursion, functions as data. Why is it beautiful and joyful? Because you have pair programming. You're never alone. You're going to have 6 exciting projects. There's a final project that you get to choose. You get to choose the project. And there's going to be a paper. And we're going to talk about that in a little bit more details. But it's called the Explore Post. And you get to explore some materials and use maybe some generative AI, which would be fun to be able to have that blessed. We also learn the big ideas of computing. We'll talk about how stuff works. We'll learn about binary numbers. We'll hear some research summaries, AI, ethics in AI, HCI, which stands for human-computer interaction, how humans and computers interact. We'll talk about the social implications of computing in several lectures. I'm pretty excited about that. We'll hopefully talk about this, how to save the world with computing, which is super cool. And maybe the limits of computing. We've decided we're still on the edge on that one, whether that's going to come in, whether we have room for that. We want to make sure to have enough time so we slow the course down from other semesters. We also want to make sure you succeed in the follow-up course if you decide to take it, called 621A. And so we teach you Python. So we're going to teach you a language called Snap and Python, and I'll get to that in a second. So we're going to start by learning this amazing block-based language called Snap. You program by dragging blocks together. It's unbelievable. You cannot have a syntax error. You can't have a typo. It's super easy and has been research proven to be more effective for learning, for beginner students to learn how to program rather than dig into a text language and get all confused with syntax errors, which means you type something wrong and then you can't read the error code. That's not what happens in Snap, and it's really beautiful and allows you to have a very graphical output. You can drag and drop images and sounds and make it multimedia in a way that's much, much easier than most other programs to be able to do that. So you'll be able to use that for your final project if you choose to do that. There's also a worldwide community of Snap users. If you have any questions, and the website is snap.berkeley.edu. And by the way, Snap was co-developed at Berkeley. So Berkeley developed the BJC course and the Snap language, and both of these act together, kind of a yin-yang, wonderful synergy. So here's how the course works. The format of the course is we're going to have office hours starting week 2. I hope you can see my cursor here. So that the format is, it's the most contact hours a week for any class on campus. It's 7 hours a week times 15 weeks, and about 5 hours a week of project and homework and reading that you do outside of class. Every single week starts this following the pattern. There's a lecture on Monday, a 1 to 2 p.m. That's where you're going to be listening to Victoria on the first, well, actually, so you're going to hear, because we don't start classes till Wednesday, you'll hear this one here this week. But normally a normal week is lecture on Monday, Hurst Field Annex A1. Then there's going to be a lab, and you have a 2-hour lab, and you can choose either the 5 to 7 or the 7 to 9. They are the same. So this blue here and this blue here are exactly the same lab. So choose one of those two that works with your schedule and then go to that. But don't go to both. It doesn't make sense to do that. Then go to lecture again. So here's the lecture again, Hurst Field Annex. And lab, by the way, is in 145 Moffett. Then you do the same thing on Wednesday. So basically Monday, that should say, yeah, Monday, Monday, Wednesday, Wednesday. So that repeats, this repeats. And in the meantime, there's all this yellow time for office hours where you can get any help on a project or a lab or practicing for an exam. It's an amazing space. We're going to have all of our TAs do that. All of our UCS1s, all of our tutors occupy 326 Soda, which is our room for the entire year. So we're excited about that. And on Thursday, come to our discussion. It's 2 hours. If you can only make 1 hour, make the first hour, but we're going to have the first hour be the normal 1 hour discussion. And then we'll have a second hour to kind of go deeper into it. So that's an optional time, but we do encourage people to come for all 2 hours if you can make it work on your schedule. And that's it. My office hours currently planned for the same time in lecture on Fridays, 1 to 2. And so we'll hopefully see you there. And I really want to encourage people to come to my office hours where we'll go over exams and do that. There are selected readings taken from this amazing book, Blown to Bits, and from websites and other things, and some videos and articles. We're going to try to have current events every lecture, in which we're going to do what's called computing in the news. We'll look into some news article that's relevant to computing and share that with you. Every single thing is free. Are you kidding me? Free? Did he say free? He said free. Free. Are you kidding me? Awesome. So this is a great course. We don't have to pay anything. We literally said, hey, we want to do this new thing. Does it cost money? Yes, but we're not doing it. So it's all free. It's amazing. And by the way, discussion is at AAPB, which stands for the Anthropology and Art Practice Building. This is Cafe Strata. This is Bancroft. It's right north of Cafe Strata. And this is the law school. So it's right near Bancroft. It's on the south side of campus. So hopefully if you live on the south side of campus, it is convenient to you. All right. What are my expectations for you? Lecture attendance is required. You need to come to lecture. We will see you in Hurstfield Annex Monday and Wednesdays. Discussion attendance is required. We are taking these things. We are taking attendance in these things. We're going to take attendance in different ways, but we'll talk about that later in each of those engagements. We're also going to try to record a video if we can. We're not sure if we can do that, but we're going to try to see if that room, if AAPB has video recording built into the room. If so, we might be able to share a video if you can't make it. But we do need you to come to these two things, lecture and discussion. And lab. We need you to come to lab too. The thing about lab is if you can't make it, then you need to do the lab before the next lab. That's the only thing I'm saying. So if we go back here, here's this lab. If you can't make these times for whatever reason, you need to do it in office hours. The best thing to do is come to lab. We have so much resources in lab. Come to lab. If you cannot make it either 1 week or all the weeks, we can still possibly work with you, but really you need to come to lab if you can make it. You can do this in office hours, and you get credit for doing the lab if you get the lab done, attendance credit if you get the lab done before the next lab. Does that make sense? You can't let you slip. You have to stay current. You cannot slip. That's the reason for ask you to come to lecture and ask you to come to discussion. That is the best practice. That's our expectation of you. Unlike this picture in Real Genius where those people all recording and I'll watch the recording later. No, do not do that. That is not going to how to succeed in this class. You succeed by coming to the lecture, coming to discussion, coming to lab, sitting in the front, sitting near your instructors and getting engaged. Don't sit in the back and go, I don't care about this. No, be engaged, sit in the front. If you need more time for projects in lab, there's an extension form. So if you ever need more time, you say, oh, I can't finish this by the deadline, ask for time. We will talk to you and do this. If it's considered late, then that means you didn't ask for an extension and we do not consider any credit, which means if you receive an extension, it's not late. If you extend, you just extend the thing. That means you got a blessed extension. If you do not fill in the extension form and you say, well, it's a day late, we will not accept it. You have to fill in the extension form to be allowed to have more time if you need it. And it's always there if you need it for every single project, which is awesome. We believe in mastery-based learning. We're going to give you multiple chances on exams. We'll talk about that a little later, but that's exciting. Are you kidding me? You mess up the first exam, you can take it again. What? Yes. Amazing course. We're really supporting you. We want to believe in this. There's more in the syllabus. We encourage you all to read the syllabus on cs10.org, which is our website. All right, let's check our enrollments. This is my enrollments when I made this slide deck yesterday, and we had open seats. Everyone was welcome to this class, including concurrent enrollment students. We believe the number of concurrent enrollment students we can fit. So hopefully everybody's coming to lecture. Everyone knows that we're going to have space for you. Nobody's on the wait list. Come on in. You're here. Now, what if this course isn't for you? There are 2 other introductory courses, and I believe they both have room this semester. The first is called Data 8. Data 8 is a course in which you're going to learn Python, just like you learn in our class. But the goal is to learn this in service of, so this is key, in service of working with data. You're not learning programming to be a programmer, you're learning programming to be used as a tool to be able to work with data, to extract it, to visualize it, to filter it, to process it, to analyze it, and to visualize it, and to make eventually some human readable documents like a graph or a chart or some kind of conclusion, okay? There's also an amazing course called CS61A. That's the follow-up course. That's the first course for majors, and it goes really fast. I'll say it again. I taught this course before, really fast. So many students start in 61A and they say, it's too fast for me, and they come back to CS10. So the earlier people know that, the better. I hope that everybody who comes back in, they're welcome. They're certainly welcome, and they need to start from the beginning and work their way through it. And we'll work with you if you've come from 61A to try to get caught up to speed. So we teach you the big ideas of computer science. Every single week is a new idea. Every single week, your brain hurts in another way. Now, this course is geared for students who have not programmed before. So if you have programmed before and you feel comfortable writing a for loop and writing maybe recursion, then you need to consider taking Data 8 or 61A. This course is geared for people who have never programmed before. We're going to go very slowly, and we're going to try to welcome everybody. So if this is you, if you raise your hand, yep, that's me, I've never programmed before, then this is the course for you. If you have programmed before, and I often ask the class and they tell me all the programming languages that they know, well, this is not the course for you. You need to be thinking about taking 61A or Data 8 because it's going to go too slowly for you and you'll be bored. And you'll take a spot from somebody who needs to be in this course. Now, this is a piece of graph I've had, which is the number of engineering graduates, PhDs in light blue, master's degrees in kind of maroon, bachelor's degrees in light yellow, and projected job openings in engineering. Notice that this is done, the sources from the NSF, National Science Foundation. So engineering, physical sciences, math and computer science, and biology. Notice that in each one of these, and I haven't shown you the number of projected job openings, the job openings is less than the sum of all the people getting degrees. Engineering, not everybody gets a job because they do other things. They might go on to graduate school or something, but they don't end up filling these jobs. Physical sciences don't fill the jobs. Biology, there's a lot of people pre-med, don't fill the jobs available. Let's take a look at computer science. Wait, what? Yes, the jobs are out there. So that's another reason to be in this course or to be in the field of computing. And again, hopefully we teach this course and you get really excited about it and you're like, I want to do more. How do I get more of this? And you take follow-on courses and you're going to be getting degree or major or minor in this course. But the job openings are amazing. Yes, the economy goes up and down, but in general, this is the graph when this data was collected. All right, let's keep going. So we're going to use Ed for asking. We're still doing red tape and still doing intro. I haven't even taught you anything yet. This is Ed for asking and answering questions, which is awesome. So Ed is our forum, and so please check that regularly and set up notifications so that you'll get notified when you're following a thread or something, and it's about that. We have some amazing staff this fall. We're so excited about this. Our UCS2s are kind of like TAs, if you will. Victoria. Ah, this is the typo. This is Victoria and Stacy. Victoria, Stacy, Marius, and Dorati. I'm sorry for that typo. That Stacy there in the second one. Rocco, Wen, Harry, Nahi, Elise, Hannah, Anvi, and Dream. And we're hopefully including more as they get added. Brian, I believe, is also going to be added to our team. I didn't have his picture, but wonderful team. And sorry, Stacy, for the typo on this. They're a great staff. UCS ones are going to be staffing the tutoring sessions in the yellow, and UCS2s are going to be running lab and running discussion and even giving lecture, as Victoria is going to be doing on Wednesday. All right, that's it. That's the red tape. Let's get started with some material. The first lecture is about abstraction. Abstraction is the most important idea in computer science, actually all of engineering. What is abstraction? It has two pillars. Detail removal, which means you remove all of the unessentials of the unessential pieces of something, the active process of leaving out of consideration one or more properties of a complex object so as to attend to others. You throw away the stuff you don't need to keep the stuff you do care about. Okay, this is a beautiful detail removal. Look at this. Here's Matisse, he looked at this beautiful woman model and he said, let me just use the shapes of it. This is cut pieces of paper. And he put this down as to capture a beautiful model who's sitting there. So this is like abstracting. Do you know what hair? Nope, you don't know what the hair. You don't know, what the complexion is, what the freckles are. No, but this is clearly a woman in a certain pose. So that's the idea. You take away what you didn't need to get the most essential pieces of it. We'll go into more detail in a second. I get it more detailed. See, I did that. Okay. Generalization. Generalization is the process of formulating general concepts by abstracting common properties of instances, meaning you don't want to have many copies of solutions. You want to have one single solution. And we'll talk about that. You want to take all these 5 examples and boil them down to one solution. That's the idea. All right. Detail removal. So I had a colleague, Professor Manish Agarwala, who's eventually moved on to Stanford. But Manish, when he was at Berkeley, worked on this amazing project, which is, this is a Google map. And if you've ever seen maybe a sketch of a wedding plan, if back in the day before GPS, people used to draw maps of each other, how to get from A to B. And they would draw these lines like this. They wouldn't draw every line in the whole map. That'd be silly. You draw only the lines that mattered. So he wrote a piece of software to automatically extract that from a map. If you said, I'm going to come and my destination's here, he said, well, how would you do this if you were doing this by hand? And his software automatically did that. So he removed the detail of all the streets in here so they only had to focus on these big streets. Now, one of the key ideas about detail removal is sometimes that's not a great idea. Most of the time it is. And so we typically do abstraction for this. But every once in a while you get stuck. Why? What would be the problem here? When is a particular case instance when the left one, Google Maps, is better than this abstract version of it? You're right. It's when, if you happen to have one of these roads, a 101, blocked, and you end up in here, you have no idea where you are. But if you actually had the map, you'd know where you were. So every once in a while, this is not the best model, but if all these roads work, this is a much better, kind of glance at it very quickly. I know exactly how I'm supposed to get to this destination. It's pretty cool. All right. So here's another example. Here is the London Underground, which is like the subway system in London. And this is in 1928. And this is after Harry Beck. Harry Beck is a famous designer. And he said, you know what? Let me straighten out all those lines to either have them be at 90 degrees, 0 degrees, or 45 degrees. And so and let me have equal distances between stops. And you get this beautiful picture, which is since 1933, we're almost going on 100 years of this is the way that they have the map of the London Underground, and in the BART system, and the New York City subway system. All of these subway systems and public transit systems typically have gone with this abstract model. Now, I'm going to ask you, is this always better than this? The answer is no. Can you think of a case when this is worse than that? Yeah, if you were going to do drilling or something, you somehow assume that the road goes, no, the road wiggles a little bit. This makes a soft turn. If I'm going to drill, oh, right in here, there's nothing there. No, it turns out that actually is where the subway line runs, because you need to know that exactly to the feet to know when you're going to drill. Am I going to drill through the subway for a new building or something? So it's mostly good. This is mostly a better usability for users. They can read it easier than all of this, which is kind of cluttered. But this is not perfect. And you remember that as an important point. So here's another example. What if you wanted to simulate a real world situation, like you wanted to simulate traffic? So you have a map, maybe you use the real map, okay? Use a real map here, and you want to simulate traffic. Do you start by modeling a car, like go into a 3D modeling program and model the car, and you model the rear view mirror, and you model the seats? No, if you were modeling traffic, you would abstract away a car to a single point, X and Y, maybe Z. So you know if you had an overhead, like an off-ramp, and you had roads that were above each other, then you would know which road the person is on. And if there's a lot of dots densely populated and not moving, it's traffic. If the dots are spread apart and moving fast, there's no traffic. So that's the idea of thinking about a simulation and thinking about a car and maybe tractor trailers. Maybe if it's a road where tractor trailers are there, maybe you need the actual shapes, because the dots, why are the dots so far apart? Because the tractor trailer is 4 times as long as the car. So maybe you actually want to have a line segment. I'm just thinking about how you might abstract away the whole shape of a tractor trailer. And sometimes they have double tractor trailers. You've seen those before, like double long. So you might have a long line, which is the size of the actual car. So you can think about how to abstract that to a dot or a line, X, Y, Z for both of those things. Okay. So you're focusing on the essence. You're thinking about what is important to you. Now, if you're thinking about whose job it is to extract all that essence to do that, is it the computer scientist job or the expert, the domain expert? The answer is the domain expert. Only the traffic engineer would know whether you need a dot or a line. Only someone, if you did some other simulation of biology, would know what are the elements of this do I need to keep to actually capture what's important about this and throw away the stuff that I don't need so I can focus on what's important, okay? So computer scientists don't do that abstracting. The domain experts do the abstracting. Okay. Second pillar, generalization. You have a farm with many kinds of animals, a dog, a chicken, a sheep, a rabbit. You have different foods for each, but the directions all look like they're the same. To feed the dog, put the dog food in the dog dish. To feed the chicken, put the chicken food in the chicken dish. To feed the rabbit, put the rabbit food in the rabbit dish. How would you do better? The answer is to feed the animal, put the animal food in the animal dish. So animal is a placeholder, almost like mail merge. Dear so-and-so, thank you so much for your interest in my company. That's like a mail merge. So that is a spot for an input. And then the possible animals would be, in this case, a dog, a rooster, a chicken, a sheep, and a rabbit. It wouldn't be for everything. Don't put bull there, because if you go, there's no bull dish. Bulls eat in this, in the field or something. So notice that this is only for some, small domestic or farm animals. This wouldn't be for all. So you might say animal, where animal is dog, chicken, rabbit, and sheep, but not these other things. So you might have some of the inputs for some cases, but not for all. So I've generalized that into one sentence. That's the idea. I had 4 sentences and I boiled them down to one sentence. So in Beauty and Joy computing, you're going to learn to write functions like y equals sine of x. We talk about function machines like a sausage maker. X is going to go in here and sine of x comes out. You turn the crank and sine of x comes out. Now, I might imagine if you had, I have one box that has no inputs. You turn a crank and it's sine of 45. The second box has no inputs. You turn a crank, it's sine of 90. The third one's sine of 120. You're like, why would I have 3 boxes that do sine of a fixed number? No, you should have an input, x. And so this x, like a function in math, this x would be the input, where x here is any angle. And so the idea is this is more general than if I had a box with no inputs that I turn a crank into sine 45 and sine of 90 and sine of 120. So as you're thinking of problems, you might think about what inputs to have for your code. So you might have code that you do that does the sine procedure. You might want to think what inputs you have. You might even think, let's make this even more abstract. Like, what, Dan? Yeah, how? Well, what if, rather than this being the sine box, what if one input was the angle and the other input was the function to do it on it? Like, what? Yes. So this could be the x, and this could be sine or cosine or tangent or cotangent. So imagine that. You can make it even more general by having a general trigonometry box. One is the actual x, the angle, and one is the actual function you're going to operate. What functions can be data? Yes, that's so cool. And this is this beautiful XKCD. It's kind of like a engineering, computer science, kind of a comic strip. And they say, can you pass the salt? And there's a delay. And he says, I said, I know, I'm developing a system to pass you arbitrary condiments. It's been 10, 20 minutes. It'll save us time in the long run. So this highlights that sometimes it's not worth it taking a box like sine and making it even more general, because you may never actually use it any more than just to use sine. If you literally ever only need sine in your application, then why put the work into making it handle cosine and tangent and cotangent if you're never going to use it? So part of that is thinking about the trade-off between the time it would take to make it more general, add more inputs that if you may never use. All right, so I'm giving you more examples. We talked about functions. How about hiring contractors? I love this example. We're almost done. We're doing well. So hiring contractors. So if you hire contractors, let's say I want to put a pool in my backyard. Well, you might have a conversation, a specification. So let me start over here to the right side. Now I'll talk about this. So in abstractions, we talk about an abstraction line, an interface. And this interface is like the contract you have with something. So the interface, the specification, or the contract. When you deal with things above the abstraction line, we only need to worry about the interface or the specification, not how it's done. So this is what it does, but not how it's done. Below the abstraction line is how it's done. And when you're using an abstraction, you don't need to know how it's done. So let me give you a lot more examples. You're hiring a contractor. What is your contract with the contractor? Well, I want to put a pool in my backyard. I don't know how much pools cost to install. Let's just make up a number. 10 grand. I want to have it, 10 feet by 20 feet, and I'm going to put it exactly there, and I need it done in a week. You say, done. You do a handshake. Now, once you do that handshake, you cannot tell the contractor how to do it. If that contractor wants to literally lug every bag of concrete and pour the water themselves, that's fine. If that contractor wants to pay subcontract, if you ever had something in your house done, this is how it works. They pay subcontractors and they do the work. Have all these people, a whole team of people come in and each one of them brings a bag of concrete. Or how about this one? How about that contractor takes a huge crane, looks to your neighbor, steals the pool from your, goes scoop, steals it and drops it in your house. Did it get done in a week? Yes. Was it 10 by 20? Yes. Did they receive $10,000? Yes. They fulfilled the contract. Now, they did something illegal, but they gave you a pool. Now you're like, where's my pool? Hey, that looks like the pool that we just had. So the point is, you can't tell the contractor how to do it. That is below the abstraction line. Above it is, that's the contract. Let's go back to sine of X. How does sine actually do the conversation? That's, I mean, how does it actually calculate sine of X, sine of 45? How does it do that? I don't know, and I don't care. That's the beautiful part of abstraction, is you don't have to know. I can use the sine function. Everyone has used, I'm sure, click the sine button on your calculator. How does it do it? I don't know. I don't care. That's the beauty of abstraction. You hide the details from the be able to use it. Isn't that cool? As you write more functions, sine X is a function. If you write a collection of functions, you might put that in a library and have that what's called an application programming interface, in which I show you, here's these functions, here's sine. Let's just say it's a trigonometry library for fun, okay? Sine of X, cosine of X, tangent of X. Here's a library. Here's how to use them. You put in a value for X and it calculates it. That's pretty easy to use. How do they work? I'm not going to tell you. That's the beauty. So I might share a set of libraries with other developers, and I don't need to tell you how I'm doing it, which is really kind of cool. It means later I can go back in and make it more efficient, and they don't need to know about it. I don't need to tell any of the users because it's below the line. Isn't that cool? It's below the abstraction line, how it works. Isn't that really cool? So that's kind of neat. All right. Technology cars. I'll talk about this I love this example. So in cars, when you push on the brake, okay, when you push on the brake, in the olden days, there was drum brakes, and the drum, it was a circle, and the drum would push on the outside of the drum. And it wasn't very efficient because if you had a really big truck in San Francisco, like a moving truck loaded with pianos, and you're going down a hill, you had to be massive, a football player, a rugby player, to have a leg the size of a tree trunk to be able to get that truck to stop. So there's always, you don't know this, but in the 40s and 50s, there's a very strong, small, very large arms with a big Navy tattoo, and they'd be huge, with chewing a half-eaten cigar, they had a big scruffy beard. That was the image of moving people, because you had to be huge. First of all, they also didn't have elevators. So they'd be moving pianos upstairs, which is insane. But the point is, that was how brakes work. And at some point they said, you know what? A more efficient way to brake is to have like a disc, like a CD, and two pads, squeeze it this way rather than pushing on the inside of the wheel. Well, that's way more efficient. In fact, if you look at you see all these fancy cars like Teslas and things, you'll see sometimes in the front, you can actually see through the grill to see the actual disc that's happening. And that's how they use it now. Disc brakes is way better than that. So that was more efficient. Did you have to tell the user? No, that was just below the line how they improved how a brake went. And now, at some point, they realized, you know what, people still had to be pretty strong to do that. Let me add some power. So there's a whole idea of power brakes. When I was in the 70s, when I grew up, they had power brakes, which means there's a hydraulic system. When you push the button, it's no longer a mechanical linkage. You're pushing a button that tells some hydraulics to do the closing for you, which means when the power was off, if you stalled your car, you had no brakes. And that happened to me, literally. I was pushing the brakes. The car stalled on my old station wagon. I'm rolling backwards over a small hill. It wasn't going to die, but I couldn't stop it. And literally the car is rolling over the hill, and I happened to hit a stop, like a stop sign or a yield sign, and it bent the yield sign, and I've saved from going down a 100-foot hill, maybe like 50 feet hill. But the point is, it was a scary moment when the car stalled and I couldn't brake. And they said, well, that's probably not a good idea. By the way, the next year, and all these changes are under the line at changes to how brakes work. The next year, they had power assist, or even if the car stalled, you could still brake it. And that's actually what they have now. They always have power assist braking. That's what we have now. How do they brake it? How do brakes work in electric cars? It's regenerative braking. How about this? They are actually regenerating. Oftentimes you'll take your foot off. It's called one pedal steering. You take the foot off the accelerator and the car stops. You are braking the car by not accelerating it. So you're not even touching the brake because it's regenerating the battery. So again, all that's below the hood. And even when you do push the brakes gently, if you push them hard, it will engage the disc. If you push it softly, it will just start the process of regenerative braking. It uses the actual engine, the actual motor in reverse mode to power the battery rather than being powered. It kind of goes either way. It's really cool. Didn't have to tell the user. Isn't that a cool thing? You didn't tell the user that this is actually doing that. And in fact, I love this example. In a drag racing, when you push a brake, you know what happens? I'll wait for it to think about it. A parachute pops out, as well as the normal braking that you have, a parachute, because it's going so fast. So again, you don't need to tell the user about all these things. These are just changes under the line that improve the experience of people above the line. Let me show one more example about the milkshakes, which is, this is an example of generalization. In milkshakes, in The Joy of Cooking, which is a famous book, if you look in the book, I'm going to ask you, do you have this in the book? On page 1, it'll say how to make a cherry milkshake. Ice cream, milk, vanilla, and cherries. Next page, how to make a blueberry milkshake. Ice cream, milk, vanilla, and blueberry, and then put it in a blender. And blueberries, and put it in a blender. Turn the page, how to make a strawberry milkshake. Ice cream, milk, vanilla, strawberries, put it in a blender. No, do you have like 20 pages of this? One page where it's exactly the same, literally exactly the same recipe, just changes the fruit? No. What does it say? Generalization. They take those 20 pages and boil them down to one page. How to make a fruit milkshake. Fruit is the input. Ice cream, milk, vanilla, insert fruit, and then blend it. And they might say not all fruit works. You put lemon in, it's going to probably curdle the milk. So not all fruit works for a kind of milkshake. Isn't that interesting? So the point of all this is, that is the idea of generalization. You summarize it all into one. I'm going to show you more examples. This is more examples. I just love these examples. Apple used to put out these power bricks, and the power bricks had an American plug here and had a plug here. And if this plug got frayed, it was a trouble. And you had to buy a different brick when you went to travel to Europe or to China or to India, where they had different plugs, or to Australia. They realized you could have a removable tip. And so this is a tip that's removable, and you can pull it out and change it for the Australian plug or the plug for the Chinese interface. So the point of this is, they realized the power of generalization. I could generalize a solution rather than having all these bricks for a world traveler who's going to be on a trip all around the world. No, you bring one brick and different tips. There's a screwdriver that has different, you might have seen there's different tips you can plug in. You have a ratchet set, different tips. One handle, very expensive handle, different tips. Why would you have all these handles? No, it's silly. So that's generalization. Isn't that beautiful? So that's an example. Let me show another example of detail removal. So I'm going to give you more examples. This is, and this abstraction border. This is a plug. This is a wall socket, okay? From the point of view of the plug, as you look into the wall socket, do you care where that power came from? Wind, maybe you do if you're green, or I'm green too, but if you care about saving the planet, which I do as well, you might care, I hope it's green power. But in terms of from the point of view of the fan using that power, does the fan care? No, the fan doesn't care where the power came from. Fossil fuels, or hydroelectric, or wind, or solar, etc., or a battery. Maybe power went out and it's being powered from a battery in your garage. It doesn't care where the power came from. Now let's actually climb into this hole. Let's climb into the hole and like an ant, and then turn around and look out. A plug comes in. Do we care what that plug is? Oh, by the way, they only care about it as long as it's 120 volts and 60 hertz of cycles. As long as it's that and it's constant, it's not going to dip, which might damage electronics. As long as it's that constant, I don't care where it came from. So as long as it adheres to the specification, 120 volts, 60 hertz, alternating current, I don't care about it. If I'm an ant looking out, do I care what utility is using my plug? Is it a fan? Is it a charger for your laptop? Is it a computer? No, you don't care, as long as it doesn't short circuit. You don't want to have a short circuit that could cause a fire. So as long as it doesn't short circuit, you don't care what, as long as the resistance is not too low, which is like zero resistance for there, as long as it's not too low, I'm happy with it. So the point of it is, oh, by the way, you also care as looking in, I care what the what the power that it gives me. Does it give me 15 amps of power, 15 amps of current to give me enough power to power my devices? So the point is, the specification is 120 volts, 15 amps of power. As long as it adheres to that, you're totally fine. Okay. So again, that is the beauty of abstraction, where you're looking at inside and outside. You're saying detail. I don't care about the details of where it came from or who's plugging in, as long as it has the specification. Exactly that. Last slide. Look at this. You got to the end. You got to the finish line. Abstraction is one of the biggest and most important ideas of computer science and computational thinking. It is founded on two principles: detail removal, take the stuff out that you don't care, like a joke. I love this example of a joke, or a movie pitch. You get into the elevator with your dean. You better have your elevator pitch of what your research is and why you need funding from them. You get into the elevator with a movie producer. You better have an elevator pitch. It's like Titanic, but with zombies and on a spaceship. Done. That is the abstract, detail removed summary of a movie you're trying to get greenlit. Okay, generalization. Take all those 20 recipes and summarize them into one thing. And so, like we talked about that in computer science, detail removal is I can use the sign procedure, the sign function, without knowing about it. And generalization is don't make sine and cosine and tangent. Make one block called the trigonometry block and have the inputs to save having to make copies of blocks. That's the idea of these functions. Okay. Now, how about this? Think about driving. How many of you know how a car works? Like literally down to the solenoid and to the, not many hands go up. But how many of you can drive a car? That's the power of abstraction. You can use these powerful things without knowing how they worked. If somebody who drove in 1930s could still drive a car today. Why? Because the same abstraction of a wheel and two pedals is back in 1930s. You know what they couldn't do? Use the radio, because now we have Bluetooth and this and it's a touch screen. You know, if in the 1930s they might even have had radio, but back in the 50s, they would have had off-on volume on the left, station selector on the right, and the middle were radio buttons. The buttons you use in computers, they're called radio buttons, came from radios in cars where you push a button to select a pre-select thing. That was it. So, and nobody, by the way, nobody back in those days used to have accidents when they would change the radio, because you could do it without looking at it. Now people have accidents because they look to the radio, because they got to touch the thing, and boop, all of a sudden they have an accident. Hopefully they don't have that, but it happens to people because they're looking away from the road. Back in the day, they didn't have that. So again, not always things perfect. To make it more abstract, oh, now it's a touch interface. Well, now it handles Bluetooth and this and streaming services from Spotify. That's great, but I have to look at it because there's no buttons anymore. So again, not all abstractions are better. Tesla is a great example. They have a screen. That screen can be a GPS or a radio selector or a video game. So that's cool to reuse that real estate on your car, but at the loss of, now I have to look at it to change it, and I can't just do it without taking my eyes off the road. So again, not everything is perfect when you have these abstractions. Okay, that's the summary of the lecture. Thank you for coming to my lecture. I'm so happy you were part of this course, BJC, the Beauty and Joy Computing. Woo! I will see you, not Wednesday because I'm in Michigan, not Monday because it's Labor Day. Have a great Labor Day. I will see you on Wednesday for the third lecture of the semester. This is the first. The second one happens on the first slot, and then I'll see you the third lecture there. Take care, everybody. All right, bye-bye.